Hello, I'm going to present the demo for research and implementation project titled HPC powered real-time disaster prediction system. In it, we will take a deep dive into a real-time disaster monitoring framework that integrates modern big data and machine learning tools, specifically Apache Kafka, Apache Spark, structured streaming, and random forest DNN-based severity prediction models. We designed this system to address the very real and pressing global challenge, natural disasters. Events like earthquakes, floods, and wildfires are becoming more frequent and destructive due to climate change and urbanization. Responding to them quickly and effectively requires real-time data analytics and intelligent alert system, and that's exactly what our framework fits in. This system is capable of ingesting thousands of disaster records in real time, processing them using HPC resources, and predicting the severity of these events using trained ML models. Based on the predicted severity, it flags critical alerts to enable early interventions. We will walk through the full architecture, code in VS Code, integrating Kafka and Spark, and then we will show how the same system runs on Google Colab across CPU, GPU, and TPU configurations with performance benchmarking for each setup. So now let us first see the our data set. We are working on a natural disasters 2024 data set. The created data set models the occurrence of natural disasters in 2024. It includes randomly produced data that sheds light on a number of disaster-related topics, including disaster types, locations, magnitudes, date, fatalities, and economic loss. The fields are all these disaster ID, disaster type. It consists of the 10,000 records. It can be used to train predictive models for preparedness and disaster management plans that we use. So it consists of 10,000 records. So let us start our project. The first part is the pre-processing of this natural disaster data. It contains some rows, some null values and rows. So with this pre-processed data.py script, we are working on the natural disaster 2024 data set here, and we are creating a new clean disasters.csv files in which the pre-processed clean data is stored, which is used for the further training the ML models and prediction systems. So the next part is the Kafka producer.py script. We are here using both natural disaster 2024 CSV and clean disaster CSV files and integrating them for the further use. First, we are training a ML model. We are using random forest regressor ML model for training the Apache Spark and Apache Consumer in VS Code, and we are using DNN model to run on the Google Colab that we will see later. So it creates a train model.pkl file which is used in the Kafka producer.py and Spark consumer script. So the Kafka layer, what does the Kafka layer do? It send times, data size, throughput, failure rate. So here we are uploading the file and it is running and it prints the following details and performance metrics, how much time it takes, what's the throughput and the total data sent, total speed, all these things. It is sending the data to the consumer and the consumer works on the trained ML model and stores the data here in a critical alert CSV file, particularly having a prediction severity. For example, we have taken the if the prediction severity is greater than 8, it is considered a critical alert and stored in the CSV file. So this is the consumer code. Here we have made the connections and define what all we have to print. So let us run the script. Here, the 10,000 datasets are start streaming from the producer to consumer from the clean disaster and the natural disaster, both files combined. So the data streaming by the producer is received on the consumer end. So here in the consumer, we will run this code, Spark consumer. So after running the code, we can see that all the data sent by producer are successfully received here. And simultaneously, when the data is receiving, it is stored in the, it is checking the prediction severity by the ML model, and the critical alerts are saving here in this in the critical alert CSV file. So it stores all the critical alerts used for the prediction. So it will run till 10,000. I have run it. So we'll stop it here as it takes a long time. So we have seen the producer code, consumer code. Also, we have two models. One is for CPU and one is for GPU. This script runs the CPU model and this script runs the trained model from the GPU. So the obviously GPU script is comparatively faster. We have run it on the both side. After getting the critical alerts, we can visualize it. Is we get all the plots which we have described here. So these are visualization plots of different disasters. As it is a time series dataset, we are using a time series plot here for disaster. It is the magnitude and severity prediction plot. We are plotting a confusion matrix, correlation heat map. So as we have seen the first part of our project, now we can implement the same in the Google Colab for the environment of CPU, GPU, and TPU and compare them. So first, let us see the CPU part. In the drive, we have uploaded the same natural disaster and clean disaster dataset here, and we have imported the TensorFlow library that is used for training the KNN model. Earlier, we are using regression model, ML model, and now we are using KNN model that is comparatively advanced and faster ML model. So here we have trained the DNN model, and the part we are using a producer and consumer. We are here simulating it in a similar way. That if the data is streamed and produced, so we are creating the same environment here, and we are printing here the performance metrics and saving the critical alerts in a CSV file. All these things happen. So in the KNN model, we are running 20 epochs. In the first round, there is 25% lost. Until the 20, it is reduced to 0.6 percentage. So these are the output of the CPU. 10,000 total records are successfully sent. There is no failure. The total time taken is the 2656 seconds, which is the fastest among CPU, GPU, and TPU. We will see further of the GPU and TPU. The total data sent is 2920 KB, and here all are the time related mean and max time information. So we got the successfully CPU implementation of our model. Now let us run the same code on the GPU. Here we have installed the necessary NVIDIA libraries graphic card for the GPU. Rapid as it was all working on a collab. We are using the collab GPU, CUDF, CUML. These all are the necessary for GPU. So we are here. We are uploading the same data set, natural disaster and clean disaster in from the drive, and working on that. We are using the same DNN model here, printing the performance metrics and creating a critical alert file, saving that CSV file. And here we can see that in CPU, the earlier time was approx 2600 seconds. Here, the total time taken is only 450 seconds. That is 5 times faster than the CPU. And also here, the 10,000 records are successfully sent and there is no failure. A critical alert CSV file is also stored in the laptop. So this is the implementation part on the GPU. Now for the comparison, we have also run it on TPU. So let us see it on TPU. We have created a TPU environment, installing the TensorFlow library for the KNN model and working on the same data set, natural disaster and clean disaster. We are running it on TPU, training the ML models. DNN model we are again using here so that we can have a same comparison on all three. We are using same parameters. We are printing the same metrics and also we are saving the critical alerts here, running the same 20 epochs. And here we can see that it has taken 1000 seconds to transmit the 10,000 records successfully and all these things. So that is the complete demonstration of our project. Thank you.